am Mr. True. In this video, we're going to start our lessons in geometry and learn about the three most basic structures in geometry: the point, the line, and the plane, and run through a lot of definitions like collinear, coplanar, intersections, find out how planes intersect with each other, if they actually even do. So we're just going to not do any problems, just lay down a foundation of vocab that we're going to need in our later studies of geometry. So, the current number of pixels in an iPad, as an example, is over 3.1 million pixels in an iPad with what, a 10-inch screen? So each one of those tiny little pixels, each one of those points, see the tie in there, is so small, or are so small, that they're nearly impossible to see with the naked eye. Yet put enough of those together and you can form lines, planes, and volume if you are talking about three-dimensional space, which we are not going to be in this video. So a point has, well, let's see here, a point is our simplest figure in geometry. It has no size, none, no length, no width, no volume. It's a point defined in space, but in pure mathematical theory, it sort of doesn't exist, but yet we've defined it. There's no measurable like object there. It's just a place in space identified. So it has zero dimension. Now I've identified a couple of points here on the chalkboard, and we of course have to represent it with something that we can see, so we put a dot which has size. And you know, it's so wide and so tall, but you know, I got to be able to see it. So at this point I'm going to identify this as point A and point B. Now with my little dots here, of course, what you might want to also identify is how are we labeling points. We label those with a capital letter in geometry. So we have point A and point B here. Now if we take these points that have no length or width, have no size, but yet, you know, start lining them out. Just think of like a pearl necklace or a beaded bracelet where each of those beads are a point, and you start lining them up. They're very, very tiny, but you start lining them up, and all of a sudden you have this line form. Or of course, you know, going back to the iPad, in this 10-inch screen that has over 3 million pixels in this 10-inch screen, of course, you're looking at it and see pictures. You might be watching me on an iPad right now, and there's a line made up of, you know, thousands, tens of thousands of these tiny little, almost invisible dots, but yet line up enough of them and they can start forming a line. These lines extend in two directions without end, okay? So it goes indefinitely. So this white, of course, is not perfectly straight here either, but, you know, forgive me on my artwork. This dividing line that I've drawn at my chalkboard to divide the two sides of notes really isn't a line because it ends and starts. So it's really a line segment, which you're going to get to. But if you're talking about a line by definition, it extends in two directions indefinitely. And you only need 2 points to define a line because it does not bend, it does not change direction. So it extends in two directions without end. It has a length, but its length is infinity and beyond. It has an infinite length because it never ends, but it does have length, a measurable, well, if you can measure infinity, but yet no width or no height. So lines are one-dimensional. I've identified this line with the 2 points of A and B. If I wanted to change the direction of this line, I'd actually have to change the position of one of these points and then redraw the line through those 2 points. And so we can identify this with notation as here as line AB. I put the 2 capital letters together and have sort of like a double arrow on top of AB going in both directions, indicating a line. Line BA, and it does not matter the order that those variables are placed, those points are placed in the name, because it extends in both directions forever. So the order of those letters don't make any difference when you identify what line you are referring to in a figure. Or, a lot of times in your geometric figures, they're going to give you a lowercase letter somewhere at the beginning or end, you know, or near one of the arrows of that line. And that means that you can use those to indicate, you know, the name of that line. So this is also line L because I have a lowercase l up there near one of the arrows. Now if you think of like taking these lines that extend for infinity, which is a collection of an infinite number of points, and you start laying them out side by side, kind of like, think of like maybe if you know someone's house or maybe your own that has a wooden deck, and you've got these big long planks of wood, these lines sort of, and you start laying them side by side. Now a line has no width, but again, if you lay line by line by line by line, and you can see it with a computer screen as well, where you can draw a line and then right next to it draw another one, and right next to it and draw another one, and eventually, though mathematically their width is non-existent, it has a zero width, but those start building up. Sort of trying to mix in a little bit of theory here without doing a real proof, but you know, you start laying them down, 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 and all of a sudden you get this plane. Planes extend without bound and have no, but yet again have no height. So where a line is just going in one direction and has a length, a plane has a length, and then you're laying those lines, if you will, sideways, so you have width as well. So you have length and width in a plane. Of course, they are also going to extend without bounds, so the length and width of a plane, that's infinity as well for each of those measurements. So, since a plane extends in two directions, actually extends in all directions, but there's no height, so just for simplicity with length and width, since it extends in this two-direction idea, sorta, really you could say it extends in an infinite number of directions, but all within the same plane, then we say it's a two-dimensional object. So it extends without bound, has no height. Planes have an infinite length and width. While there is no true edge, we have to draw something. So you'll normally see planes represented in geometric figures or drawings as a parallelogram. But you could draw a rectangle as well. But you know, we draw a rectangle or usually a parallelogram, and somewhere in there put a capital letter, and thus this is plane M. Of course, because we have, again, draw something, so we generally make them look like parallelograms, but indeed they are not, because parallelograms do not extend with length and width forever. Let's get to the next screen. We're going to define collinear points, coplanar points, intersections, and so on. So let's get to the next page of our notes. Let's get those definitions started. Space, the final frontier, and also in geometry is the set of all possible points, or the set of all points, excuse me, in the whole universe, the space. Collinear points are all in the same line. So collinear points, remember, a line is going to be straight, it doesn't bend, it doesn't change direction, it's a straight thing, a straight line that extends indefinitely in both directions. Now it only takes 2 points to define a line because it does not change direction, and therefore, you know, it's straight. If I have 3 points that are sharing a line, there's a lot of theorems that we're going to learn in geometry, or a handful of them anyway, to show that that a collection of points are collinear. I'm going to pull a reference that you know from algebra, which is just using slope. Because what I'm saying, you know, a line is straight and does not change direction. Slope that you learned in algebra, which is rise over run, describes the direction that a line is taking. So if I've got 3 points here, A, B, and C, then the slope from A to B is equal to the slope from A to C, which is equal to the slope from B to C. I've collected all the different variations that I can find slope using these 3 points, and they're all the same. They're all equal. So those 3 points do all fall within the same line. And of course I have to give you a non-example. So these points of D, E, and F, you can see a sharp bend that I would have here if I tried to connect. Let's see, if I tried to connect D to E and then to F, I would certainly not get a figure that appeared to be straight, and therefore it's not a line. And they're not collinear. Coplanar points, as you might now guess, are points that all share or all fall within the same plane. So I've just simply drawn a plane M here and identified 3 points that are inside that plane. And here I've drawn a green plane, sort of going in this left-right direction, even though of course they extend indefinitely, where I have the points of D and F inside that plane, and then coming through from a different direction, maybe, let's see here, just to give you more of a three-dimensional example, I've got this plane here, DE, and it holds the points DE, and then I have another plane coming in and intersecting it that has this point F. I'm trying to identify those with different colors to, make my diagram most legible. Hopefully those colors are showing through up on the camera. So DE are in this green plane, point F is in the yellow one, and therefore these 3 points together are not coplanar. We interrupt this regularly scheduled program to bring a correction because, well, while I am correct 98% of the time, I am wrong the other 3%, and who cares about that? Probably you, since you're watching this video to actually learn something. So I'm about to say, or just said, that these 3 points are coplanar and these 3 points are not. That is a problem because 3 points define a plane. Just think of, well, my camera's on a tripod right now, and those 3 points where the tripod is touching the floor, basically those 3 points are defining the plane of the floor. So saying that these 3 points are coplanar is no big deal because, well, 3 points define a plane. So my problem with my example I just did is I need a 4th point. And now let's make a big deal. Hey, look, I've drawn these 4 points and they're all in the same plane. So these are coplanar. D, E, and F, while my drawing has been made purposely to attempt to make them appear to be in separate planes, I could draw a 3rd plane that is defined by these 3 points. It would kind of come in here at an angle, and I would sketch that really quick, but it'd be kind of ugly on this diagram. So let me introduce a 4th point, and then I can actually say, hey, look, these 4 points are not coplanar. So let's, this one plane here that I said was going in the same direction of the board, let's call this D, E, F, and let's put a point G over here. And so the points of D, E, and F are defining this plane that I've drawn sort of horizontally and kind of just sort of like a rectangle. And then this point F, if you see this intersection line, it's kind of like this, I'm trying to make this point here in this plane coming out of the board kind of appear to be in front. So it's almost like point F would be kind of like out here, and points D, E, and G are actually on the plane of the chalkboard, okay? So now I have 4 points that are not coplanar. I've got 3 points that are on the same plane or in the same plane, and 3 points define a plane, so that's always the case. We have D, E, and G. Those are in this plane right here, and point F is in this diagram not in the same plane. It's on this other plane coming in front, and it's actually sort of out here in space in front of the chalkboard. Now, getting back to the rest of our video. Over here we have an intersection, just like an intersection in roads. It's where 2 roads meet. Oh, on the intersection of blank and blank. Same thing in geometry. Where 2 figures cross each other, intersect, well, they intersect. So, intersection of 2 figures is a set of all points that are in both figures. So we have a line L and a point A that is on that line. So it's an intersection here, right here at this green dot. So point A is either in or on. The language is interchangeable. Line L, capital letter for the point, and the lowercase letter indication for the line, don't forget that. Or line L passes through A. Now, if I were to introduce a new point, like say, here is point B, I can draw that point up there near line L, but there is no intersection because, of course, line L is not going through that point the way it is drawn. If 2 points, if 2 lines intersect, then they intersect at a point. Now, 2 lines don't have to intersect. There'll be a definition coming up later that you should recognize from some of your algebra studies, parallel. Parallel lines do not cross. They go in the same direction. You don't have to have lines be parallel for them not to cross. They could be in other planes as well. So if my 4 arms are lines, they could be one going in this direction and one going in this direction, but this arm is in front of this arm, so these lines are not intersecting. They could be parallel, be in the same plane, but also not intersect. Again, these definitions in minute detail, very specific detail, are coming up later. But if they do intersect, they are going to intersect in a point. I have plane H drawn, and I have a couple lines working with this plane H. I've got a line going through it, so I have line L going through plane H. I'm trying to identify it's going through because you see here the line is solid, sort of like, let's see, well, let me get a pencil. I can have this, plane, which is my piece of paper, and this line, or this line coming through it. Well, if the line is sort of between your view and the plane, it's going to be solid. But when that line comes through the plane and falls below it, you're not really going to see that line. But we draw these dotted lines to represent that, we understand that this blue line is solid. It's passed through the plane, and I'm just making it dotted so to show representation that it's, still there. It's just sort of behind the plane so that we can't see it. And then, of course, we make it solid after the view of it goes beyond the edge of the plane that we draw. Now, again, remember, planes don't have an edge, but we have to be able to draw something. So as that line comes back from behind the yellow plane, we're going to make it solid again to indicate that we can, clearly see it. And then we have this green line K, which we're going to draw as being in plane H. So we have K, line K, we know it's line K because it's lowercase, and capital P, so that's going to be a point P. We see it right here, that's the intersection point between the line and the plane, H here. Lowercase k, line K and P are in plane H, and line L intersects H at P. This line K right now is in the plane. So again, let's see here, paper and my pencil. So this could be plane H, and my line is literally like in it. Now you can have a line be above a plane as well and not be contained within that plane or intersect it. That's not what I have drawn here, because we're defining intersection point, identifying ways that different geometric figures, these lines, planes, and points can intersect and contain each other. I've here got two planes drawn. I'm trying to, of course, give some depth to my two-dimensional drawings on this flat chalkboard. I have plane B and I have plane A sort of coming in here at an angle, and they are intersecting at a line. Planes, again, do not have to intersect. I can have a two-dimensional plane here and a two-dimensional plane here. They can be parallel and never intersect. However, these planes are intersecting, and they're intersecting in line C. If two planes intersect, they're always going to form a line. Now, with the CD, with this line segment here, the planes extend in all directions, or, well, not all directions, there's no height, but the planes do extend in length and width forever. You could argue that that's every direction if you stand there and just kind of, sort of rotate and look out. And the lines extend in both directions forever as well. But again, we have to be able to draw a plane somehow. So please, again, for one more time, like this line, this looks like a line segment, something we're going to define in a minute. But because it's an intersection of two planes, it is going to extend in both directions forever. So planes A and B intersect in line CD. Keep that double arrow indicator above the CD. If you don't indicate that, it means something else. It would be the length of a line segment. And we're not measuring length. And both plane A and plane B contain line CD. Hope these definitions are making sense for you. Let's get to the next page, which is going to be, looks like just some examples. So for our series of questions here that we're going to use as our examples before finishing up the video, I've drawn attempted to draw a three-dimensional sort of house figure here. And what I did was I drew a five-sided figure, a pentagon, and flat horizontal base, two vertical sides, and then a peak in the middle. What I attempted to do to draw this as best I can is I went off of each one of these corners. I picked this one first and went in a certain direction for a certain length. Then what I tried to do was I went to the rest of the four corners, 5 total, and I tried the best I could. I can see here there's a little bit of separation here with these two lines, but I tried to go off and make 4 more lines that all went in exactly the same direction, parallel. And I also attempted to make them the same length. I didn't use a ruler, probably should have. And if you do that well enough, if you draw your front face, and at least that's what I would do with this figure, draw my front face and then go off each one of the corners in making parallel equal line segments, and then sort of just connecting the dots in the back, remembering to put some dotted lines to represent those lines that are at the back of the figure that if it were solid you wouldn't really see, to make the figure. So that's a tip on how to try and draw it. We want two planes that intersect in line RS. Now RS is this line here that is at the top of our sort of house, if you will. And all these are an intersection of a lot of planes. So what two planes that intersect for, that extend in all directions, or, sort of in this two-dimensional plane forever, what line do they, and they intersect to form that line RS. So it wouldn't be AB, that's the base of this house. This right-hand side here, FBCG, is extending vertically forever, so that's not going to intersect line RS. It's the two, basically the two sides of the roof. Plane RFGS, you can name a plane with 4 letters when they're drawn in this fashion. And I don't have any, it would be too confusing to throw more letters in there to be able to identify the plane as a single letter or with a single letter. So plane RFGS is coming and leaning in from the right, and plane ERS, and see that H back there? That plane is leaning over to the right, and together they're coming to form that line RS. So again, it's plane, and you can do that with a little parallelogram figure as well. So plane, what was it? RFGS. And plane, I was going to write a P, plane ERSH. Okay, 3 lines that intersect at H. Well, let's see, where's H? H is this back corner here. So I needed to identify a line with 2 capital letters, don't forget the double arrow on top, that come together and touch or help to create or intersect at that point H. So RF is in the front of this house, that's not going to ever intersect. H is in the back, and so we're going to have EH, so line EH with my double arrows, line SH, and last but not least we have line DH. Now you see there's no, again, just one more time, none of these lines have arrows extending in both directions. They look like line segments where they stop. But this diagram is supposed to represent, and we are talking about the intersection of planes. So that's why they're being described as lines, and therefore being extending on these lines extending in both directions forever, because the planes extend forever as well. 3 planes that intersect at C. So 3 planes can intersect. If they do intersect, 3 planes can intersect in a line. They can also intersect in a plane, or at a point. So let's see here. Point C is in the bottom right-hand corner, and that point here at C is made up with the plane on the side of this house, if you will, the base or bottom of the house, and then finally this back plane that we have drawn, looking at the moment like a pentagram, or a pentagon, excuse me. So we have, let's see here, plane. And I'm going to use the same sort of generic parallelogram notation for all 3 of these planes. It doesn't matter that the back has 5 sides. So let's see here. BFGC and plane ABCD and plane DHSGC. Please note as well, as I'm naming off these planes, I'm not trying to jump around. I'm not saying that this this plane is A, C, oh let's go here to B, and then back to D. I'm going around the corners in sequence. It's really very important. It's even more important really when you're identifying like an actual parallelogram or rectangle. We'll be dealing with those later. Okay. By the way, 3 points define a plane. So one could argue that I could maybe name the bottom with, say it's plane ADC, but that would be confusing because it would kind of seem like that there was only 3 points there. So I'm using all 4 corners, but 3 points do define a plane and 2 points define a line. Are A, D, and C coplanar? Are those 3 points in the same plane? Well, let's see here. A is right here. We have D, which is sort of following along the this sort of bottom left-hand line here. So we have A and D; those are in the same line. And C, well, let's see here. A, D, C. All of these points are helping to make up the bottom plane of this sort of house-like figure. So yes, indeed, those 3 points are coplanar. Now what about R, S, and C? R's here in the front of this house, if you will. S is in the back, and C is also within that back plane. So the back plane here contains the points of C, G, S, H, and D, but point R is in the front of this three-dimensional sort of house figure. Again, it is hard to see on a chalkboard, which is two-dimensional, that this is, but we're trying again show some depth with the fact that all the angles are kind of like in this sort of parallelogram, leaned back sort of kind of diagram, and of course with all the dotted lines, again trying to emphasize the fact this is a three-dimensional object. So R, S in the R's in the front plane of the house, S and C are in the back, so the answer is no, they are not. Name 2 planes that do not intersect, 2 planes, if you will, that are parallel. Well, let's see here. The right side of the house intersects with the bottom plane. The front plane coming down here vertically is going to intersect with this one that's sort of flat. We need 2 that do not intersect. Well, with this, we want to look at either the front and back plane because they're looking, sort of like this, where they're not going to intersect. So the front plane and the back plane are not going to intersect. So planes A, E, R, F, and B, that plane is not going to intersect D, H, S, G, and C. So that would be a possible answer, the 2 pair together. Another possibility would be the left side and the right side, because those are, well, unless this is, convergent in the back, those are not going to intersect as well. It does not appear to be in this diagram. So plane AE, HD, okay, that's the left side of this house, if you will, and the right side BFGH. That would be another possible set of answers for the last question here. Name 2 planes that don't intersect. So I hope I've helped your understanding a little bit on points, planes, and lines. That's in my video. So I'm Mr. Drew. Go do your homework.